Hello, friends. Welcome to AP Week. I hope you're all doing well. This is our last installment of a little AP Chemistry review today. So welcome, welcome. Let's dive ourselves in. So today, as promised, we were just going to do a little problem solving. All the concepts that we needed to cover, we've covered in the last 5 or 6 weeks or so. I had promised to kind of look ahead and use my crystal ball, but as it turns out, the College Board saved me from myself in that they actually published some of their review problems. So my plan today was just to kind of go through those. I plan on doing that. If some of you are sitting out there saying, oh gosh, I've already gone through all of these, one, sorry, might help to hear my take on it, I hope. And also, I suspect that it won't take me a full hour to kind of go through these. So what that means is if you have questions that you've been dying to ask over the last couple weeks, but haven't had the inclination or time to do so, now is the time. Feel free to use the little Q&A button there, launch a question. Happy to use whatever time I have left at the end after going through these to answer or talk about or make up questions about whatever you'd really like. We'll dive in, go through the College Board stuff, and then see what kind of questions that you guys have so that we can make sure we get you the answers you need before test day. By the way, I've heard checking out Twitter and Reddit, heard about some people's experiences today. It seems like the vast majority of kids aren't really having any problems at all. Sure, there are a few who the upload tool didn't work, but it seems like that's the vast majority and might have even just been user error on their end. So knock on wood, so far so good for day one of the online AP. You should definitely check out the online demo tool, however, if you haven't taken an AP already this morning, and make sure that you're comfortable with the interface and how to use it so that won't be a barrier between you and doing your best come later this week. Alrighty, well, let's dive in with these problems. So sample question 1. For those of you who haven't seen it, and by the way, all of these can be found on the College Board website. We'll give you a moment to read through this. Right, we've got additives to drinking water that pipes contain lead. When Cl2 flows through a metal pipe containing lead, some of the lead atoms oxidize, losing 2 electrons each, and aqueous chlorine ions form. Write a balanced net ionic equation. Okay. That sounds good, and it's actually not at all like the net ionic equations you're used to seeing. In fact, it's easier than that, really, because what have we got? Well, we've got lead solid and it reacts with chlorine gas. Well, lead loses 2 electrons, just like they told you to become lead 2+. And then we get 2 chlorine ions, 2 Cl-. Is that a balanced equation? Yeah, the charges are all balanced. Is it a net ionic equation? Well, is there anything left to dissociate? Not really, right? The lead's solid. The Cl2 is aqueous and doesn't dissociate because it's Cl2. So that is the net ionic equation. So as I've heard reported today, from at least some of my physics kids, they weren't exactly overwhelmed with how complicated it was. So try not to make easy questions like this more complicated than they need to be on test day. The second part, okay, Ksp values, and we remember that Ksp is just the solubility product, right? It's a lot like a KEQ. So Ksp values for 2 lead components are given in the following table. Write the Ksp expression for the dissolution of lead phosphate in water. Okay, well, what does the lead phosphate break up into? As you can see, it breaks up into 3 leads and 2 phosphates. So the Ksp expression is very simply the concentration of lead 2+ cubed and the concentration of phosphate 3- squared. Do I put it over the concentration of lead phosphate? No, I don't, because that's a solid, and if we recall, those don't play in our equilibrium constant calculations. Part C. calculate the molar solubility of lead phosphate. Okay, so the molar solubility versus the Ksp, right? You should be comfortable going back and forth. If they give you the molar solubility, you should be able to find the Ksp. If they give you the Ksp, you should be able to find the molar solubility. In this case, we have the Ksp and we want the molar solubility. So if we think about this reaction, right, some of the lead phosphate, pardon me, is going to dissolve. And how much of it dissolves? Well, that's the molar solubility, right? How much can dissolve? So how much is that? I don't know, let's call it X. Well, if X of those things dissolve, how much lead have we got? Stoichiometry tells us there's going to be 3 times that much, and how much phosphate, stoichiometry again tells me 2x. So if we rewrite our Ksp expression now, including the Ksp we're given, that ridiculously small number, is now equal to 3x cubed and 2x squared. I know it kind of seems redundant to kind of include the 3 in both places and 3x cubed and the 2 in both places and 2x squared, but that's exactly how you do the problem. You'll notice here that the numbers work out super prettily because 3 cubed is 27 and 2 squared is 4. And if you multiply that, you get 108, which looks oh so much like the 1.08 on the other side. So that when you divide, you simply have x to the 5th equals 1 times 10 to the negative 55th, which, by the way, you can almost even do by hand and find that that's 1 times 10 to the negative 11, right? So that would in fact be the molar solubility. The solubility of lead phosphate would be 1 times 10 to the negative 11th molar. A reasonably more difficult question than certainly part A or B, but still not that bad at all. Alrighty, using that table of Ksp values, explain why the addition of phosphate is more effective at reducing lead in drinking water than chlorine. Well, if we look back at that table, right, what's the Ksp of lead phosphate? Well, a ridiculously small number, 10 to the negative 53rd. Lead chloride, much, much larger number, right? So we would expect then that the solubility of lead phosphate is much less, right? So it would take less phosphate, right? Since the Ksp is much lower, it would take much less phosphate to precipitate out the lead. It can be a little deceiving though, because depending on how many parts those things break into, the lower Ksp doesn't always mean the lower molar solubility. But here it certainly does, because the molar solubility we already calculated, heck, it's already less than the Ksp value of lead chloride, right? So that's why we know it's more effective. Okay, let's put that to work and do another slightly tweaked math problem. We want to maintain the maximum dissolved lead concentration at 1 times 10 to the minus 9th. Okay, we already have a concentration there. That is the current concentration of lead. And now we're going to add enough phosphate at a new concentration. Basically, would the amount of lead increase, decrease, or remain the same? Justify your answer with a comparison of Q and Ksp. I'll remind you, right, the Ksp, while we wrote an equation for it, Ksp is the number we look up in a book, right? The only thing we can change Ksp is the temperature. Right. Q, however, I can calculate at any condition. So Q is basically what we call the solubility quotient, right, in this case. And that's just the Ksp expression evaluated at whatever conditions I happen to be at, right? But before we even dive into this, let's use a little intuition, right? Why would the lead concentration increase, decrease, or remain the same? Well, if I've gotten enough phosphate, well, some of it might precipitate some lead out. So the lead concentration could decrease. Well, if I don't have enough phosphate, well, maybe then nothing will happen, right? It's hard to imagine how the lead concentration, however, might increase. That would not be a very good answer. So let's do the math and see whether it's decreasing because there was a precipitate formed or whether it remained the same. So let's calculate our Q and compare it to our Ksp. So the Q expression looks just like the Ksp expression, right? Lead cubed, phosphate squared. So if I pop those numbers in, I get something like 9 times 10 to the negative 37th. Is that greater or lower than the Ksp? Well, that's greater. right? So if Q is greater than the Ksp, what does that mean? Well, in solubility or in equilibrium terms, right, when Q is greater than the Ksp, I have too many products and not enough reactants. So the equilibrium will shift away from the products, or in this case, to the left, back to the solid. So we will get more of a solid precipitate. So with more of a solid precipitate, then we're losing lead concentration in solution, so that lead concentration should absolutely decrease. Alrighty, moving on to the next part. Higher concentrations of lead are found in pipes carrying hot water than in pipes carrying cold water. Is this observation consistent with a negative enthalpy of dissolution, delta H SOLN? Justify your answer with regard to Le Chatelier's principle. Okay. So we're given a delta H, and you know the letters beyond the delta H, don't get so upset about, right? You might see delta H RXN for heat of reaction, or delta H SOLN for heat of solution. Basically, it's the enthalpy change of the reaction. In this case, the reaction happens to be something dissolving, so we call it a delta H of solution. If it were the reaction involving something burning, we'd call it a delta H of combustion. But really, it means the same thing. So here we know that that thing is negative. Alrighty, great. So what does that tell us about this reaction? Well, that it's exothermic, right? So that's going to help us answer the question, right? If delta H is negative, that means it's exothermic. So what does that mean? That means that if you were to add heat here, where would heat be? A reactant or a product? Well, it's exothermic, so heat would be a product. So increasing temperature is kind of like adding more products, right? Which way would that shift the equilibrium? Well, the Chatelier's principle says that a system at equilibrium, when exposed to a stress, will shift its equilibrium to relieve that stress. I've added temperature, added heat, if you will, added a product. So that means we're going to shift back to the left. So shifting to the left, would we expect that to increase or decrease the lead concentration? Well, we'd actually expect it to decrease the lead concentration. So that observation is inconsistent with what we would expect. The AP is definitely going to throw some curveballs like that. So don't be afraid when you're saying, oh gosh, am I supposed to like get the answer that this explains that thing? Well, maybe, or maybe those higher lead concentrations have, I don't know, something to do with leaching the lead out of the pipes. That could be it. Right? So there could be other competing effects here. So trust the chemistry, trust the rules you know. Don't like try to get the answer you think they want, because that's not necessarily going to help you here. Okay, on to the next bit. So again, we're seeing them try to roll lots of different concepts into the same question, but none of those particular concepts are honestly particularly hard. Here we've got some Lewis diagrams. Great, thank you. Using diagram 1, the student claims that the bond angles are 90 degrees. Do you agree or disagree? Well, we've got a Lewis structure in front of us, and how do we know what shape it is using VSEPR theory? Well, we look to see how many areas of electrons are hanging off that central atom. In this case, there are 4. Are there any lone pairs? Nope. So just 4. So if you recall from our VSEPR chart, that was a steric number of 4, which we know should actually lead to something that looks tetrahedral, right? That's the way nature solves the problem of spacing 4 guys out as far as possible while still having them bonded to the central atom, right? So would we expect that to be 90-degree bond angles? Nope, we wouldn't. We would expect those angles to be a whole lot closer to 109.5 than 90 degrees, because those are the bond angles for a tetrahedron. So again, you know, no is in fact sometimes the right answer on this test, so don't be afraid of it. Another question on this same stuff. The student finds that all 4 bonds have the same bond length. Which diagram is consistent with this finding? Justify your answer. Again, fairly common sense. Which figure or which diagram looks like all 4 bonds are the same? Clearly diagram 2, right? But we definitely want to justify our answer with a little more kind of chemistry than just saying that, right? So what we might say is that, you know, the 4 bonds have the same bond length, so we would expect them to have the same bond order, right? Which is a fancy way of saying single, double, or triple bonds, right? Because we know that bonds of different orders have different lengths. So that would lead us to diagram 2, and yes, we can see that the bond length of of a first order or a single, you know, phosphorus oxygen bond is 163 picometers, which is real close to 162.5. So obviously it's going to be that diagram 2 rather than diagram 1. And then finally, or almost finally on this question, the student generates the following particulate diagram. And remember those particulate diagrams, which we talked a lot about, just cartoons of the molecules, that's all. You know, the student uses dashed lines to show hydrogen bonds. Okay, so there are hydrogen bonds. Well, one of them's wrong. Which one? Well, that should be pretty clear to those of you who've been paying attention, because remember, hydrogen bonds are bonds between what? Between a nitrogen, oxygen, and fluorine, and a hydrogen bonded to a nitrogen, oxygen, and fluorine. So obviously here, the bond labeled A, I believe, is sitting there between a hydrogen and a phosphorus. Is that a hydrogen bond? No, it's not. Why? Because, well, honestly, that phosphorus there is not sufficiently electronegative, right, to generate the attraction needed to be called a hydrogen bond. And that phosphorus, even if it were nitrogen, oxygen, or fluorine, it's not one that's already bound to one of the hydrogens, right? So no hydrogen bonding there. The other ones are all between hydrogens and oxygens that are bonded. And then I believe finally here, we have a photoelectron spectrum. I think we talked about these way back in week 1 or 2, maybe. Week 2, I think it was. A student notices the rightmost peak of oxygen is taller than the rightmost peak of phosphorus. The student claims that this is because of the occupied electron shells, which means that the valence electrons are closer to the nucleus and experience greater attraction. Do you agree or disagree with the student's claim? Justify your answer. Okay, well, this one might seem somewhat compelling because the student is kind of making sense, right? Well, oxygen, the highest occupied shell of oxygen, is closer than phosphorus, right? It's the n=2 shell, not the n=3 shell. But if you kind of remember what a photoelectron spectra looks like, or honestly, just read the axis here, the y-axis says relative number of electrons. So the height of that peak isn't really about the attraction to the nucleus. It's really about how many electrons there are, right? So even though the student's claim, kind of the student's point about oxygen and phosphorus is correct, it is not a good explanation of why that peak is higher. Why that peak is higher is simply because phosphorus, if we think about where that rightmost peak is, right? If we just kind of imagine the electron diagram for phosphorus, right? The peak on the far left is the 1s shell, then the 2s, then the 2p, then the 3s, and then the 3p, right? So that rightmost peak for phosphorus is the 3p, which contains 3 electrons. Well, oxygen, however, if we count 1s, 2s, 2p, the 2p in oxygen has 4 electrons. So it's really about the greater number of electrons in oxygen's 2p compared with phosphorus's 3p, right? That's what the height of those is about. Okay, and that wrapped up question 1. So, you know, you had, what, 25 minutes to do that? Doesn't seem super crazy. I'm talking real slow because I'm doing a webinar, and we did that in less than 25 minutes, explaining way more than you'd have to explain. On to question 2. Methanoic acid is a monoprotic acid that can be synthesized by reactions between CO and NH3 in the presence of hydronium ions. Hey, wait. I thought they said acids and bases weren't on this test. Well, titration curves and things like that, buffers aren't on this test, but, you know, acids and bases kind of all over chemistry. So like I said, you'll definitely want to be comfortable with the basic ideas of what an acid and what a base is and how they neutralize each other, even though the certainly more nuanced aspects aren't going to be covered on test day. So here we're given a 3-step reaction mechanism and the overall reaction, much like we've seen in our earlier weeks together. And they want us to know, they want us to write a chemical formula of the species that behaves as a catalyst. So remember here in our mechanism, right, we've got reactants and products, clearly. But then we also have things called intermediates and things called catalysts, right? Intermediates would be chemicals that are created and then destroyed as part of the overall reaction. So here, the product of step 1, HCO2CH3, that will be what's called an intermediate. Why? Because it's created in step 1, but then it's destroyed in step 2 and does not appear in the final reaction. So created then destroyed, intermediate. On the other hand, something that was present from the beginning that was destroyed and then created again would be the catalyst. And that here clearly would be methanol, right? Because methanol is there in step 1, but it gets eaten back up, or I'm sorry, it gets eaten up in step 1, but then spit back out in step 2. So it doesn't appear in the overall reaction, but it is in that first step. So that's a catalyst. Okay. According to the proposed mechanism, if additional ammonia is added to the reaction mixture, will the rate of the overall reaction increase, decrease, or remain the same? Justify your answer. Okay, well here we basically need to find what order is the reaction relative to ammonia. If it's first order or second order, well then we know that increasing ammonia will increase the rate. If it's 0th order or maybe even negative order, that could change. So how do we find the rate of a reaction? Well, if we have a mechanism, we start by writing the rate law of the rate determining step. And we remember that the rate determining step is the bottleneck. It's the slowest step. Here, that's simply step 1. So I can write the rate of reaction by saying R equals K times concentration of methanol to the first power times the concentration of carbon monoxide to the first power. And I get to do that, if you recall, because it's an elementary step, right? It's a what you see is what you get. And I can use the stoichiometric coefficients in my rate law, which I cannot do for a full chemical reaction. Okay, in a more complicated problem like the one I gave you last week or 2 weeks ago, right, we had intermediates in our rate law, which we then needed to use a steady state approximation and do all sorts of fancy stuff. We actually don't need to do that here, right? Yeah, sure, there's a catalyst, which might bother you a little bit, but really the rate of a reaction is determined by the rate or determining step, clearly, and also it can be influenced by any steps that happen before that rate determining step. Any steps that happen after really can't mess with the rate, right? So here, ammonia doesn't enter the scene until after the rate determining step, right? So the concentration of ammonia here will have no, change in the concentration of ammonia, pardon me, will have no effect on the overall rate of this reaction, right? Might seem odd to you because it is certainly a reactant there, but this reaction will be 0th order in ammonia. You know, there are more nuanced questions they could ask, right? Like, how does changing the rate or changing the concentration of methanol affect the reaction, because it's not even a reactant? What's going on there? You'll notice they chose not to ask about that, right? If you study enzyme kinetics in biology, you'll know that there are several different regimes, and it kind of depends on the relative concentration between methanol and CO, and it can get a little complicated, but they've totally stepped around that, right? We don't need to know any of that. We just need to write the rate law, rate determining step, notice that ammonia is not in it, and just be done. So moving on, a student generates the following potential energy diagram for the overall reaction. Is this diagram consistent with the enthalpy of change of the overall reaction? Well, if we go back, what was the enthalpy change here? It looks like negative 81 kilojoules per mole. That would be endothermic or exothermic, people. We know now that a negative delta H is exothermic, which means heat is released. Well, if heat's released, where did it come from? Well, if heat's released, it must mean that the energy of the reactants is greater than the energy of the products, and that extra energy gets released into the surroundings. Another way to think about it, right, is that delta H, whenever you see delta anything in chemistry, it's always products minus reactants, right? So that means the enthalpy of the products minus the enthalpy of the reactants is negative. So it must mean that the reactants have a greater enthalpy or potential energy here than do the products. And that is not at all what is shown here. What's shown here is backwards, right? So this is inconsistent with what we're seeing for our delta H. Again, don't be afraid to say that the claim is wrong. It happens a lot. Okay, and moving on to the next part here, we get some intermolecular forces. Definitely expect some IMF questions. At the end of the reaction, HCOOH is separated from CH3OH by distillation. If you happen to remember, distillation, right, is a separation based on differing melting points, or I'm sorry, boiling points, pardon me. Right, I raise the temperature until one of the species begins to boil, the other one doesn't, so the one that gets boiled turns to vapor, runs through a distillation column, condenses somewhere else, and thus I've separated them. So distillation, separation based on boiling points. Here the question is, identify the types of intermolecular forces in these two compounds. Well, I see a whole lot of carbons, hydrogens, and oxygens, and whenever I see hydrogens bonded to oxygens, I think about hydrogen bonds. And there are definitely hydrogen bonds, and both of them will hydrogen bond with themselves and in fact with each other. They'll also, of course, have London dispersion forces. Everything has London dispersion forces. You never want to ignore that, right? You don't need to say dipole-dipole interactions because hydrogen bonding is a particular kind of dipole-dipole interaction, so your bases are covered there. But even if you think that, oh, the hydrogen bonding is more important, which may or may not turn out to be true. But even if you think that, you still want to mention the fact that there are London dispersion forces, whether this thing is polar or nonpolar or whatever. Okay? Because the next question is going to build on that. When an equimolar mixture of these two compounds is heated, the vapor phase contains a higher mole fraction of methanol molecules. Explain this result. Well, really, when we're saying the vapor phase contains a higher mole fraction of ethanol, or methanol, pardon me, we're just saying that the vapor pressure of methanol is greater. Okay, well, what does that mean about the intermolecular forces? Well, in order to vaporize, in order to go from that liquid phase to the gas phase, what did we need to do? Well, we needed to overcome intermolecular forces. So if there are more methanol molecules in the gas phase, that must mean the intermolecular forces there were easier to overcome. So higher vapor pressure means weaker intermolecular forces. So how can we argue that that's true? Well, we said they both hydrogen bond and they both have London dispersion forces. So why would one be weaker than the other? Well, LDFs are a really good target here because we know that the strength of London dispersion forces has everything to do with how many electrons a molecule has, right? How large it is, how many electrons it is. The larger it is, the more electrons it has, the more polarizable we say it is, and the stronger the London dispersion forces are. So here, the larger molecule, which is also, by the way, a longer molecule that has more surface area, another contributing factor, it's not surprising that that guy would have a lower vapor pressure because it has stronger intermolecular forces, particularly stronger London dispersion forces. Got it? Good. Moving on, again, they promised that the acid-base chapter wasn't on the test, but that doesn't mean acids and bases aren't. So here's an acid-base question for you. The student uses sodium hydroxide, you should recognize that as a strong base, to titrate methanoic acid solution of unknown concentration. So we do have an acid-base titration question, albeit an easy one. A balanced chemical equation for the reaction appears above. The student places 20 mils of methanoic acid in a flask and uses a burette filled with 0.3 molar sodium hydroxide to deliver just enough sodium hydroxide to reach the end point. The incomplete data for the student's 3 trials are summarized in the table below. Calculate the molarity of methanoic acid from the student's data for trial 1. So the end point of a titration, right? Often evidenced by a color change and an indicator and all of that stuff that's not on the test this year. But we don't need to worry about it because we're told that it was the endpoint. We don't need to worry about how that endpoint was noticed by the student. We just need to do the math because we know that at the endpoint of a titration, what's true? Well, the amount of acid or base that I've added equals the amount of base or acid that I had. So I simply said the moles of acid equal to the moles of the base. Right? And we know that here we're not directly measuring moles, we're measuring things like volumes. So how does that relate? We know that the number of moles is simply the molarity times the volume. So we get this equation, which is often called our neutralization equation for obvious reasons, because it shows when the number of moles of acid equals the number of moles of base, we have a neutralization. Here, conveniently, 4 variables, We know the values for 3 of them. We solve for the remainder, right? I'm solving for the molarity of the acid. I know that 20 mils of acid have been added. I know the molarity of the base and the volume of the base. So very simply, we can find, just through some quick math, 0.25 molar methanoic acid is the concentration of that unknown acid. Yeah, sure, it's a titration problem, but it's a pretty easy one. And finally, the last question or two, a simple one. Hey, here's the burette, what's the reading? Right, you should know by now, always measure from the bottom of that burette, and the burette has a 0 at top, which means this is something like, I don't know, 18.18, somewhere between 1 and 2, closer to 2. Remember that last digit is kind of the one that's insignificant, where there's a little uncertainty. So just make your best guess and it's gonna be fine. I can't imagine they dock you for 18.17. So finally, the student calculates a value for the concentration of methanoic acid for trial 2 that's significantly higher than the value for the other 2 trials. And he says that the reason is that, oh yeah, some water remained in the flask to which I added the acid, which means I had to add more base in order to neutralize it. Do you agree or disagree? Hopefully you disagree, because what did we say the endpoint was? When I've added enough base to completely neutralize the moles of acid present, right? In this case, if the student has some extra water lying around in that beaker, will that change the number of moles of acid present? I don't think so. It's going to dilute it, but that's really not going to affect our calculation because the same number of moles of acid are present, which means I need to add the same number of moles of base to get to my end point. So I think it turns out that we actually disagreed with students more than we agreed there in terms of their claims. So definitely don't let that be a problem for you on test day. So now I will invite any and all of you to submit whatever questions you'd like. Like I said, I thought we were going to finish up a couple of 15 minutes early. So if you'd like to hang around and ask some questions, I'm happy to give you particular answers to your particular questions. Otherwise, it's been fun. I wish you guys nothing but the best of luck on your AP chemistry test this week. Feel free to hit me up afterwards. Let me know what you thought. Hopefully this finds you very well prepared. But again, make sure you do some practice problems. Make sure you practice with that tool so that you can strut your stuff on Thursday like I know you're all going to do. Have a great day. Why are molecules that exhibit hydrogen bonding soluble in water? Okay, so you've probably heard this about a million times. Like dissolves like, right? So if a molecule hydrogen bonds, well then it's going to hydrogen bond with itself, but it's also going to hydrogen bond with the water molecules, right? So you can imagine a molecule like HF or something that hydrogen bonds will kind of work itself into that network of hydrogen bonds that water is creating with itself. A nonpolar molecule, however, won't be able to do that. A nonpolar molecule is going to massively disrupt that network of hydrogen bonds that water is trying to form. So if you can imagine, you know, a bunch of nonpolar molecules all scattered throughout a solution, right? Because that's what it would be if it were dissolved, right? They'd be randomly scattered throughout. Well, that would disrupt hydrogen bonding everywhere. And that would result in a higher energy. So what happens is all of the nonpolar guys kind of segregate themselves together to get the overall system to a lower energy, because all of the water molecules can then happily hydrogen bond with each other, lowering the overall system energy by kind of shunting all the nonpolar guys off to the side. And that's really what we mean by insoluble. They don't mix. Something that hydrogen bonds can weave itself right into that hydrogen bonding network. And that's why we have the principle of like dissolves like, right? So something that's nonpolar dissolves other things that are nonpolar very well. Something that's polar dissolves other things that are polar very well. That makes sense for you? Awesome. Anyone else? Other things I'll mention while you're getting the gets to type of question. Please make sure you get a lot of sleep the night before this test, right? The last thing I want you guys to do is stay up late at night cramming before this exam. right? You already know, I suspect, a vast majority of what you need to know on test day, right? The last few days before the test should not be about cramming more and more information into that brain of yours. It should be about putting yourself in a position so that you can adequately and accurately show all of the things that you do know, right? So no cramming the night before. Night before, you know, eat your favorite food to the extent that you can get your hands on it right now. You know, stream a couple episodes of real bad television, go to bed, right? You do probably want to make sure that your books are in order and your resources and whatever study guides you created are kind of laid out where you can put your hands on them easily the next day. So make that part of it easy. You know, get up in the morning, have yourself a good breakfast, and go rock this test. And have yourselves a great test. If I can do anything for any of you between now and test day, remember, I'm Aaron. I work at PrepMatters. That would make my email address, aaron@prepmatters.com. Feel free to reach out. More than happy to answer questions via email. Other than that, go kill this thing. Bye.